Hey, check this out. C equals 2 pi r. Put a bunch of these together and you get the height of a three-dimensional figure. Add in the area on top and the area on back and you get the surface area for a three-dimensional right cylinder. Okay, so let's say that we're asked to find the surface area of a volume of revolution of sine x from 0 to pi. And the volume of revolution is going to be about the x-axis. And of course the obvious reaction is to be like, oh my god, surface area of a volume of revolution about the x-axis. But we can actually go about this in a rather simple manner. Remember before the c equals 2 pi r. That c, of course, is talking about the circumference of this disk. And what we're doing is we're putting them all together. Now imagine taking these disks, c equals 2 pi r, and then stacking them up right here like this along the graph of sine x. We take the circumference of each disk and then we multiply it by the number of disks. No different than finding the surface area of a cylinder. Exactly what we're going to do here. These are going to represent all the little CDs that I had, and the tricky part is going to be to add up the number of CDs that we have. Okay, so I've blown up sine x right here, just a small part so we can analyze what's going on. So when we add up all the CDs, it's actually going to be the length of this curve. Okay, so let's say we wanted to find out the length of this piece right here. Let's say between these 2 points. Well, if you're thinking Pythagoras and unit circle, that's exactly the route that we're going to take. What we can actually do is draw a triangle right here, a right triangle, that we have this right triangle and that this hypotenuse is going to be pretty close to the length of our curve. And we know what these two sides are. This is our delta x, and this is our delta y. So we know that this c squared is going to equal our delta x squared plus our delta y squared. This c is equal to the square root of all of this business. And just so that you're clear on this, that c is going to be the width of our CDs, and then what we're going to want to do is we're going to want to add them all up together. That c is not the circumference yet, it is just stands for the c in the Pythagorean theorem. But we'll get to the circumference. We're getting there. We're close. First we have to add up all these CDs. Okay, so now we're here, and we want to add all of these up. But this is where the mathematical hocus pocus comes in. Remember the mean value theorem that states that the instantaneous slope of any specific point is going to equal to the average slope over an interval? Okay, so here's where we're really sneaky. This mean value theorem has this y2 minus y1, and that is delta y, which is exactly what we have right here. So we can rearrange this for our delta y, which is what we want. So this delta y is going to be equal to our f prime of some c, which we can just denote as x, f prime of x times our delta x. And this is really where the beauty comes in. This is really the crux of it all right here. Because when we rewrite this, using our definition here, plus f prime of x times delta x, and remember that it's squared because our delta y is squared. Well, look what we can now do. We can take a delta x squared out of this whole thing, and that is phenomenal because look what happens. We take out this delta x squared and we get 1 plus, oh, too excited. We get this 1 plus f prime of x squared. Look, since we have this delta x squared, this can actually come out of our square root. And then when we take it out, this becomes delta x times the square root of this 1 plus f prime of x squared. And that is just a beautifully simple formula. When we take the limit of the summation of all of these, it just becomes an integral, and that's good to know, but I can just write it here just to save some time. What we end up with is this integral of this crazy square root function that actually works. Remember that all of this was just for the length of our curve, which is really the number of CDs or the width of these CDs, however you want to think about it, that makes more sense to you. I like to think of it as the summation of all these little CDs, because this delta x is representing their infinitesimally small width, and it just helps me when I think about them as we're just adding up the number of these CDs rather than thinking about the width, because the width is really negligible. but when you put them together, you get like a width of like 3 millimeters or something. Just to come back to this formula, it's so cool because this is actually the arc length from A to B. So if we plug in, say, an A and a B, say this were A and B, what this would do is it would add up all these little individual CDs here in between, and we would end up with a number that would be the length of this curve right here. Pretty crazy. And just to recap all the craziness that we just did, we got this arc length formula by taking the summation of all of these little quadratic formulas that we got from right in here. All of these little quadratic formulas, we took the summation of them using some crazy mathematical hocus pocus, and then we got this. But definitely understand the mathematical hocus pocus and how it was used, as this really makes it make a lot more sense when you know that like this is where this crazy substitution came in. That just blows my mind every time that we can think about that. So now that we have the number of all of our disks, the last thing that we need to do is find their circumference of each of them. And so now we just need to figure out what is our r. Well, r, if you'll recall, since we're rotating these around this x-axis, our r is going to actually just be our y value, which is, of course, our f of x, which in this case is sine of x. C equals 2 pi r, and our r equals f of x. And we want to add all of these f of x's up too. We want to add up all of these y values. So the thing that we can do is we can actually just put it right here into our integral. So when we add this f of x up, we're going to put that into this integral from a to b. So now we have the integral from a to b of 2 pi r, which is our f of x, times this business right here of our arc length, because we wanted to know the length of, or the number of CDs that we have. We wanted to know the length of our CD stack. And this is our formula that we really care about. So now, of course, we can use it for the easiest part of all. So plugging it back into our original problem here, we get the integral from 0 to pi of 2 pi times our f of x, which is sine x, and now just right here on the next line, times our square root of 1 plus our f prime of x squared, and our f prime of x, the derivative of sine x, of course, is cosine x, and that is, of course, also going to be multiplied by the ever popular delta x. And we don't actually need to solve this out, we have calculators for that. I'm just going to put it into Wolfram alpha. Comes out to be approximately 14.42. But this number doesn't even really matter. The fact that we figured out this crazy surface area of revolution formula is really what is very important here. And I hope you enjoyed this derivation as much as I did.